Yeah, now today I want to give you an overview of, uh, you know, variety of different areas where we've seen that incorporating different kinds of structural constraints into neural networks, as well as other forms of domain knowledge, greatly enhances learning and generalization and robustness, and also provides some tools that make this easy to do. So I will hope to give an overview, and you can look into material for lots of details and further deep dive. Yeah, so the main idea is when we are thinking of learning from data, there's also the other aspect, right, which is the priors. What other priors do you add in addition to data? And priors can be very simple in terms of, say, the use of convolution for images, which is an inductive bias, or could be much more involved, such as, say, laws of physics, if you want to design control applications, right? Like you're not learning from scratch, you already have the knowledge of Newton's laws of motion, and you would use that. But then some aspects could be hard to model, such as the aerodynamics, and that's the one you can use data to learn a good model for landing, like we have done. Could also use priors like tensors and graphs. I know graphs are very popular and also the topic of this set of sessions. And what we see is this is natural in many settings, and I'll show you later on how we can use graph neural networks to model molecules, right? Like be able to calculate quantum level energy calculations for molecules, very precise calculations, and how we can use graphs, but also other forms of domain knowledge to do this quantum level calculations. Simulations are another form of priors. I mean, simulations could also be in form of data, right? You're feeding in now synthetic data or simulated data instead of the real data, or in addition to real data. But also simulations could be in the form of how you set the parameters in simulation. And it could be the full sim to real loop and back to sim. So those are all examples of priors that we can utilize, and many, many more, right? So learning is not purely data, right? There's always some prior knowledge we are building in on how to select, say, the hyperparameters, how to design different layers of the network. But I feel that if we do that more thoroughly and in a principled way, we'll get even better gains in terms of good generalization, sample complexity, and good also potentially robustness. So those are the aspects that I'll now give some more details on. So in the first part, I want to talk about tensorial neural networks, how using tensors we can get much better generalization, but also compression. So tensors are extensions of matrices to more dimensions. I think this is something hopefully everyone in the audience has heard about tensors. If not, you can think of that as multidimensional generalizations of matrices, right? So just as matrix has rows and columns, with a tensor, you can now have an array with multiple dimensions. But it's more than just an array, right? So just as matrix is not just an array, but an operator, in fact, a linear operator, similarly, tensors generalize matrices to get multilinear operators. And so we can think of primitive operations on tensors that extend matrix products. And that's the tensor contraction, right? So in matrix product, or in this example of matrix vector product, you multiply the matrix, right, along the columns here in this example. And now if you want to contract the tensor, you can do that along all its different dimensions, right? So this pictorial depiction, I think, gives you a natural generalization of matrices to now tensors, and now matrix products to tensor products. And so if we are now extending BLAS operations in, say, GPU or CPU or other hardware, we can build now very efficient implementations of tensor contractions. And that's where, NVIDIA is looking into these very efficient operations without doing transpose and other expensive operations. So NVIDIA Q-Tensor is one such library that gives these primitives of tensor contraction sped up in GPUs efficiently. So there's also the hardware angle of this, that these tensor contractions can be much more efficient and fast compared to matrix operations. So we are getting the power of parallelism much better with tensors. But in terms of how it helps learning, what we found is the tensor methods are very effective to compress neural networks, right? Because if you're now having a better inductive bias, you can have a smaller set of parameters. And you can also be much more robust. In fact, we've found tensor dropouts to be much more effective than dropping out on matrix layers, and indeed ultimately good generalization. So the idea is, it's not just bigger is better philosophy, right? That's what we've seen, say, with language models. Everybody's advertising how big their language model is. I mean, we've now gotten to trillion parameters. And while that's impressive in terms of engineering those systems and seeing what they do, that's not the only realm, right? We have to keep in mind that ultimately, by providing better structure and inductive bias into those neural networks, you can have cases where the smaller network is much better than a bigger one. And that's what we've seen repeatedly with our use of tensor methods, that we get a much uh, better generalization, but in a compressed network. So you're getting best of both the worlds in this scenario here. And not just both the worlds, but multiple, right? Here you see the four facets of it: better compression, good speed ups in hardware, a good robustness, and generalization. And this is where Tensorly is an open source framework in Python that gives you an easy uh, way into using tensors. So you can start from any of the backends. PyTorch is the popular one, right? You could also use MXNet, NumPy, JAX. So these are all aspects that you can have the flexibility in. And then there's different core tensor operations, such as, like kind of tensor transpositions, transformations, and then decompositions. But ultimately, for deep learning, the aspect we made it very simple and easy is the Tensorly-torch that's exclusively for PyTorch. And here the goal is we have ready to use tensor layers, right? So if you want to now design a neural network architecture, you can just directly import these layers. And we've done a lot of optimizations there and set good initialization and other parameters, so you can use this out of the box. And so that makes it very convenient for everybody to start designing architectures that involve tensors. And it's also, we have like tensor dropout. We can automatically set the rank of the layers, like, of different tensor operations. So we have the initialization set. I apologize, these bullet points for some reason are not showing up. But there's a lot of nice properties in terms of what Tensorly-torch already has. So just as an example for this, what we see is you if you want to now define a PyTorch layer with, say, Tucker tensor representation. So for those who are not familiar, this is where there is a core tensor and then factors, right? And you can now uh, use this as a way to have compressed network. So this, you can set the rank, or you can let um, our heuristics set the rank, but this leads to compression and better inductive bias. So ultimately, you can, decide like kind of few simple things like what is the input size, output size, and yeah, and the rank. If you just set it to be the same, then our approach chooses the rank. So here you see a simple way to define this layer, and then you can combine it with other layers that you like. And so we also have different forms of tensor representations. There's multiple notions of tensor rank. So CP, tensor train, all these are ways that you can compress layers and you can decide what is the right approach. And so this was the example for regression. So meaning last layer, you can compress using a tensor regression approach. You can also do that in convolutional layers. You can, take your regular convolution layer, right, the standard one, and then you can either use a pre-trained layer. So you start with a convolutional network that's already trained, right? And then you can say, I want to compress it. And if you say zero point 0.5, you compress to half the parameters. So that's a convenient thing, right? Because many times you already have a default model and you want to further compress it, and this provides a way to do that. Or you can also just train from scratch if you don't have a pre-trained network, and then you can specify all different sizes and get the different orders and so on. So so a lot of flexibility in terms of how you can define these factorized convolutions. And you can also do it in different architectures, whether it's ResNet, MobileNet, and so on. So all these are, as you can see, already made, right? You just have to have one line and it's done. And so the convenience of it is what we hope the community will utilize to explore how these networks are effective in a variety of different scenarios. So as an example of how tensors are helpful in different tasks, one challenging task is long-term video prediction, right? So not just the immediate one, but prediction into the future. And that is where we see that convolutional tensor train LSTMs are very effective. So what we are doing is temporally, we are now forming a tensor train. So instead of first order Markov model like an LSTM, this is a higher order Markov model. And the higher order Markov model with tensor trains helps it compress. So you can choose the rank of compression. And by doing this, here you can see that early detection is something convolutional tensor train does much better compared to other models. So it's able to detect this activity much faster compared to the other models. And this is the message, right, that I said earlier, that a bigger model is not always better. So our convolutional tensor train LSTM model has much smaller number of parameters than the earlier state of the art. Here you can see like it's 20x, right? So nearly. And in that setting, we are still doing better, right? So in terms of different video quality metrics, in terms of long-term prediction. And so this aspect, I think, is something to really emphasize, that don't always think of just making the network size big. Instead, incorporate structure and domain knowledge to potentially also have compression in addition to better generalization. So that was one aspect that I wanted to emphasize. There are many other scenarios where the use of domain knowledge can be very helpful, and that's what we've seen in this latest work on how to learn PDEs effectively, right? I mean, indeed, this is a huge area, and right now, traditional solvers are slow; they're not data-driven, right? So each time you need to slightly change things, you need to recompute everything, which is very expensive and time consuming. So can we use data-driven approaches to speed up solving PDEs? So one important aspect that we realized was this requires the approach of operator learning, right? So meaning not just map a finite dimensional function input to a finite dimensional output as in a standard neural network, but potentially have infinite dimensional mappings from input to output spaces. I mean, that's how we define the notion of solution operators in solving PDEs, right? So you can have arbitrarily sized inputs, so the arbitrary grid, arbitrary resolution of input, and the corresponding output solutions. So we want that flexibility, that it's not limited to one grid or one resolution. And that's the new approach that we have, that it's independent of that. And also it learns for the entire family of PDEs, right? So if you're doing Navier-Stokes, we'd like to be able to uh, use a fixed neural network to now solve any different specification. So you change the input conditions, boundary conditions, you don't have to retrain the network. That's the main difference compared to other approaches that use neural networks to learn PDEs, because we want to get the solution operator for the entire family and train it once and then use it for all settings. Otherwise, it's way too expensive. You'd slightly change the initial conditions, or say shape of your aircraft wing. You have to redo everything. You have to do expensive training. That's not a good approach in our view. And so that's the idea, right? So the input is a set of coefficients. The coefficients can be these initial conditions and boundary conditions, and the outputs are solutions. And these coefficients can come at different resolutions of grid points, right? I mean, ultimately, you should be able to evaluate anywhere you like. You specify these are the input conditions, and then what is the solution here for the PDE. So we want that flexibility. And there are multiple instances of training, right? So here you can see for the entire family of PDEs, we can now vary different initial conditions, boundary conditions, and look at what are the corresponding solutions. And here we are using the domain knowledge, right? So there's a lot of work done over decades on building good solvers. And so what approaches do they use, and what inspiration can we obtain from them? And that has been so critical to our success in this area. And thanks to Andrew Stewart and Kaushik Bhattacharya, who have decades of experience in the area of PDEs, who are our collaborators. And what we see is, in this canonical form of PDEs, right? So what we see is, if we had a linear PDE, we can express the solution operator in terms of Green's function, right? So this is a very standard and natural approach. So it's like convolution with the Green's function gives you the solution for a linear case. And our intuition was, for nonlinear cases, what you would like is composition of many such layers, right? So, and that's what we uh, see here, that we can lift the input to some space, and then, use the kernel, right? So kernel convolution, and then do some nonlinearity and keep composing many layers of that. So ultimately, what we show is this is a universal approximation for any operator. So we are now extending the notion of neural networks from finite dimensional spaces to capturing operators potentially in infinite dimensional spaces. So rather operators that model mapping between infinite dimensional spaces. And the other aspect that really helped us, right, that came up only a bit later, this wasn't the first work, but a later work that we did, where we saw that Fourier transform was the best approach for convolution. Because unlike images which have sharp edges, these PDEs that we are considering, like Navier-Stokes for fluids, is very smooth but has global convolutions, right? And so we need that Fourier transform to capture all these different wave numbers or frequencies. And so that's how we can now approximate this kernel convolution in each layer. We can do the Fourier transform. And so convolution is just multiplication with the matrix in the Fourier space. And then we can do the inverse Fourier transform, right? And so once we do this, then we have this, it's a linear operation. We can do nonlinearity and we can proceed over multiple layers. And that's the approach we took. And the idea here is this is not dependent on the grid or resolution, because we can do Fourier transform in any resolution and potentially on any grid, right? So that's what gives the flexibility for the approach. And what we see here is this is the first method that can solve Navier-Stokes PDEs efficiently with very low error, and be able to do that by training on very low resolution data and directly evaluate it in high resolution. So this is 256 by 256 size here. And what we trained on was just 64 by 64, right? So you can train now in low resolution and directly get high quality, high resolution answers. And even like the time resolution, we trained on a much lower resolution than the resolution which we are evaluating. And so you have this flexibility and you have the ability to capture all these complex eddy currents and turbulence in fluids effectively. And so now we can do this in all kinds of different initial conditions. We can use this for inverse problems, which we did, and we could speed that up almost up to 1,000 times faster. So this has real world implications in terms of the ability to solve PDEs efficiently and replace traditional solvers. So that was, I think, a great example of how domain knowledge helps, because the notion of Green's function and the notion of how to describe solution operators gave us a principled approach to designing entirely a new framework for solving PDEs. In many other cases, again, domain knowledge has been very helpful. And this we see with the use of graph neural networks to model molecules. And this can be seen in the broader realm of drug discovery, material discovery, right? I mean, especially in these times of pandemic, we see the power of quick discovery of drugs and vaccines. And this is certainly not the last pandemic, right? So we'd have to be very agile in being able to quickly discover this. And that requires searching over a huge space of molecules, right? So here you can see chemical compounds, it's order 10 to the 60, right? I mean, this is just nothing close to feasible in terms of brute force search. So you would have to be very strategic, and you also need fast methods to be able to calculate properties very quickly. And that's where the approach we are taking is to ask what are the right features we want to capture. And you can just do it from scratch, right? You could take like a structure of the molecule, say all these different molecules, compute their energy, compute their solvability, different properties, and use a standard network to fit that, right? So you can map that input to the output using a neural network. That's straightforward. Or you can use a graph neural network directly on the molecular structure, like the graph, and connect neighboring nodes, neighboring atoms, and learn an embedding and map it to the energy and other output properties. The challenge, though, is if you train this on a few molecules like this, you can't expect that to transfer to, say, protein molecules, right, with thousands of atoms. And that's because uh, the energy of bonds in a molecule is not just dependent on neighbors, but on the entire molecule, right? So it's not just a short-term dependence, short-range dependency of only nearby atoms. And that's where the domain knowledge here really helped. I mean, this collaboration with Tom Miller's group at Caltech, what we see is, there's notion of molecular orbitals that is cheap to compute. This is a traditional approach of getting features. But that tells you how far you need to go in this molecule to get neighbors for a graph neural network. Like, what is the influence of an atom here on the other atoms in the molecule? So you can compute that range now using molecular orbitals. And that gives us now the neighborhood for constructing a graph neural network, right? So very simple approach in the sense of now instead of putting neighbors, just the neighboring atoms into the graph neural network, we're now using molecular orbitals to determine who should be the neighbors in this graph neural network. And yeah, and then we can combine it with the framework of graph neural networks and learn embeddings. And what we see is this can give us DFT level computation. So DFT is the standard approach for getting very precise quantum level calculations, density functional theory. And ours is able to uh, speed that up, right, thousands of times. The exact one is like the force field version of it. So we are getting like very good predictions of properties, but also speed ups, right? So, and the many other we have tasks shown. This is just one example. So we are able to predict all kinds of properties for molecules, which is very important for drug discovery, and do it very fast. And the key is, again, we only trained on small molecules here, size up to, I think, 30, and we've like tested it on molecules 10 times bigger, right? So again, the same approach of zero shot generalization to larger molecules. And that's only possible because of the inductive bias we have with molecular orbitals, right? So we've used the domain knowledge to construct very transferable properties or rather embeddings to now evaluate on entirely new molecules of much larger sizes than in training data. And this is so critical, right? So this theme comes up again and again with the scientific applications. Getting data on, say, large molecules or high resolution PDEs is very expensive, right? So if you could do that with cheaper data, data that is cheaper to obtain, then that's great, right? Because you've reduced your training costs and you can directly evaluate it on much more complex scenarios. And there is no way that a standard neural network would be giving you this because it just cannot, right? It's only generalizes on the same kind of training and test distributions. And that's where we need that extra to obtain good transferability and zero shot generalization to larger problem instances. So the other aspect that I want to emphasize where structure is important is for compositional reasoning, right? So here the structure we can think of in terms of concepts, or symbols, right? Like using a neuro-symbolic approach would be now where you're incorporating additional structure of symbolic reasoning into your learning. And that's very critical if you ultimately want to do some form of robust inference. And this is also true in our brain, right? When we are doing rational thinking, the system too, that involves compositionality, that involves reasoning. And so ultimately, we want to see our learning progress from just representation learning to now compositionality and reasoning. And indeed, right, so in our lives, we have all kinds of examples of composition, whether it's composing music or art, you're taking simple concepts and composing them in creative ways. And what we've recently done is constructed a new benchmark for concept learning called Bongard logo that appeared in NeurIPS recently. And the idea is, can we, challenge AI methods to discover concepts and carefully measure their ability to do this? If you give lots of data, right, neural network can learn the concept well. But that's not interesting, right? That's already been shown. So what we'd like to see is if it's only given few examples. So here we can immediately see that, on these set of examples have sharp edges and these don't, right? So it's very easy for us to capture this concept the moment we see it. So if we provide lots of such problem instances of few short learning, how well does the neural network do in learning concepts? And that's what we did in this work on Bongard logo. And this is inspired by the classical challenge of Bongard, which was hand constructed with few hundred problem instances. But then we wanted to scale it up because, it shouldn't be that the data is so tiny that standard neural networks cannot learn, right? So we wanted it to be systematically generating as much data as we like, but at the same time, it keeps the challenge, right? We make sure that neural networks don't overfit and easily learn, spurious correlations and do well. And so the way we took care of this was to ensure, I mean, we did different kinds of shapes, first of all, but the most important aspect is we wanted to capture three core properties of human perception and cognition. The idea is we want to, ensure that humans can do well on these challenges, but then these aspects of human cognition is very hard for machines to currently mimic, and hence we can carefully test their concept learning abilities. So if you see here, this is a set of positive examples here in the columns A, and here these are negative examples of a concept, right? And similarly, this is a different problem instance. In both of them, the same shape appears. But then, depending on the context of these other examples, the property that is being utilized or the concept that is being utilized is different. Here, the property that it shares with other concepts is having 4 straight lines. Whereas here, the property that it shares with other concepts is having 6 straight lines. So here you can see that you can describe the same shape in different ways. So it has different concepts, but you have to be now reasoning, right? Which of those descriptions is apt for me to compare it to these other examples, right? Because they're all sharing the same concept. So this is the thing that's very important. And if you just did pattern matching, it'll completely fail, right? Because it's the same pattern in both these problem instances here. So that's something to keep in mind. And the other is compositionality. So here you can see that simple shapes now compose together to become a complex shape. This is something we have very good abilities to capture. Can we test that? And ultimately having infinite vocabulary. So all other previous challenges tend to have very small vocabulary, like just a set of fixed shapes, like the clever data sets, right? And we wanted to make sure, that's not a limitation, because ultimately, if you're having infinite vocabulary, as you generate more problem instances, you will still be challenged, right? You cannot overfit. And that was something we wanted to have. And what we see first of all is different meta learning approaches, all the state of the art. It's still far away compared to humans, where the expert is somebody who carefully looks at it, is in the 90s, right? And even the amateur, you can see, is not far off here, at least in these kind of shapes. So there's a big gap. And the other is, what we saw was neuro-symbolic approaches did the best. So having now an action program here, an action decoder, like trying to understand the generative model, right? Like how is the shape generated? What is the set of program commands? Having that helped it across the board to do the best compared to the other approaches. So having the structure of symbol grounding was very helpful here. And of course, in a general sense, how do you come up with good neurosymbolic approaches is an open problem. So that's what we saw here. So to conclude, I showed you many different examples of infusing structure and domain knowledge. I introduced Tensorly-torch, which has ready-to-use tensor layers, and you get benefits of compression, generalization, and robustness. And you can use it in a variety of scenarios. We also saw neural operator that learns the PDE solution operator in a resolution-free manner. And again, the domain knowledge, knowing how we can construct solution operators for linear PDEs and then think of nonlinear PDEs as compositions of that, was great. And then the OrbNet used the knowledge of molecular orbitals to capture the neighborhood in graph neural networks. And this was very critical for transferability to large molecules, larger than what we see in training. And ultimately, the Bongard logo challenge poses a very principled approach to few shot concept learning. And we see that neuro-symbolic approaches are doing the best. And there's still a lot of gap with human level cognition. So it's a lot of, hopefully this challenge will be useful to others who are aiming to bridge this gap. Thank you.
So thanks, Professor, for the presentation. So we have a question from Professor Sriram Natarajan. So, Professor, would you like to ask it on live?
Yeah, thanks. Thanks for a great talk, Anima. Quick question. So there's a lot of, because I work a lot with medical domains, you get a lot of knowledge in the form of qualitative constraints, like how Boutillier or Benjamin Kuipers would have written it. So A and B, as A increases, so for instance, as BMI increases and your cholesterol level increases, the length of stay in an ICU unit for COVID will increase. All right. So we get these qualitative statements which are like borderline causal statement, A and B causing C. What is your intuition on how this can be encoded in a tensor? Like when you guys talk about domain knowledge, it's fascinating, and I want to see if such knowledge can be encoded in a probabilistic model. You just constrain the CPT or your distributions, and then you're done. But here, how do you do it? An intuition would be great.
Yeah, that's a very good point here. So you want to capture some kind of monotonicity or some properties, right, among the...
Yes, or synergy, for instance.
Yeah, and yeah, so when it's qualitative and not, because if it's monotonicity, you could still try to embed that, right? Like through order relations, you could, capture that as a constraint. But again, if it's not, yeah, so it depends, right? So what kind of qualitative constraints they are. So I would say that monotonicity can be captured, right? Because you can, you know, the very basic approach would be to like do data augmentation, right? Like kind of like look at show different examples of changing those features, keeping the others constant. And if you could like look at what the network and then constrain the network so that the monotonicity is met, right? So you put a penalty term, so you can train on some form of like, say, contrastive loss, right? Between like positive and negative examples to meet that relation. So that's one approach. Hope that makes sense.
Yeah, yeah, that does. Thank you. Thank you.
So we also have one more question from Archit. So do you want to ask it on live?
Sure, I can ask it. So I actually have like a couple of questions because a lot of your work kind of overlaps with areas of my interest. Thank you for the great talk. So I was just curious, like how do you specify the rank of the tensor? Because if you have like a higher order tensor, say order 3 or more, it's very hard to figure out what the exact rank is. And the follow-up of that is like, how do you do these low rank decompositions of such tensors, like inside your like inside Tensorly?
Yeah, so there are, we have multiple methods for tensor decomposition, alternating least squares, score method. So there's a whole kind of suite of methods, right? And sure, I mean, all these problems are NP hard, right? There are
Right.
cases where the rank is not well defined, but those, in most kind of typical cases, it's okay, right? So there's always the issue with non-convex optimization and particularly tensors. And we have different notions of tensor rank, right? So we have Tucker, CP, tensor train. So you can use these different notions depending on the
I
application.
see. I don't know if I have time because I had another follow-up, like different question on your ARBNet thing. So like when you work on DFT, do you actually compute the constant potentials in that particular case?
So first of all, we are not using DFT, right? We are comparing it with DFT. So
Ah, okay,
yeah,
sorry.
all we do is compute only molecular orbitals, and then use that in our graph neural network. So those are the features we start with, and that's why it's very cheap compared to
I
all.
see. Okay. Thank you so much.
So we have another question from John. So if you're online, you can ask it. Okay, so the question goes like this. So from a practitioner's point of view, would Tensorly-torch be competitive against TensorRT acceleration for image tasks like object detection?
So first of all, they're not competing against each other, right? You can use both together. So Tensorly-torch is to define these tensor layers and either retrain them, or in our case, you can start with also pre-train layers and compress them. And then you can use TensorRT on top of that.